So let's look at a proof of the reflection principle. This is we're going to have 3 steps, and the first one is maybe the most crucial. It says that if we find the Brownian motion uh, at time t, if we find it above the level b, then the first hitting time of that level has already occurred. And so, we're sitting here at time t, and let's say the Brownian motion took, there are 2 paths here, or kind of 2 alternative paths. One went, it's above the level b here, and so, if we do find the Brownian motion is above the level b, the path is continuous. It started at 0, so it's no wonder that the point at which it crossed that level had to have happened before time t. The only way to get here is to cross this line, and the crossing point had to come before this current time. You can also convince yourself that the converse to this statement does not work. The converse would read, if the first hitting time is smaller than, comes before time t, then the Brownian motion is above the level b. That's certainly not true. So you can think of this alternate path for the Brownian motion that went downwards here. And so here we find the Brownian motion below the level b, and yet nevertheless, it managed to reach the level b at an earlier time point. So the converse is not true. You can kind of negate both things. So if you have if some property, then another property, then not this implies not that. That's certainly true. We can kind of verify it. If I guess here you would have, maybe I can place time t like so. So time t, let's say, precedes the actual hitting time, or in other words, the hitting time is larger than time t, which is the opposite of this statement. And obviously we find that the Brownian motion is strictly below the level b, which is the negation of that statement. If the first time is after whatever present time we're looking at, there's no way we would have reached the level b simply by the definition of the very first hitting time. So what does step 1 give us? It gives us this inclusion. It tells us that the set of events on which the Brownian motion exceeds the level b at time t is a subset of this set, which says that the first hitting time is smaller, came before time t. And the implication of this is significant. Here's what this implies. This is an intersection of 2 of these sets, and one of them is a subset of the other. So this event and this event, you have an intersection. The intersection of 2 events, one of which is a subset of the other, is just the smaller subset, and therefore this equality holds. So the left hand side equals the right hand side, and this is really the key to the whole proof. The rest is sort of a little bit mechanical. So let's run through the calculation here. So here's the second step, where I'm going to pick up with this probability but write it in the form of expectation of indicators. Those are the same. The probability of an event is the expectation of the indicator, and here the probability of 2 events is just the expected value of the product of the 2 indicators. Same thing. What we're going to condition on, so we've transitioned to the expectation to use the Tower property, and what I'm going to condition on is the first hitting time itself. And when I know the first hitting time, so the first, in the first part of applying this, the expectation would have maybe included both of those. It would have included both of these indicators, and this one was taken out of the expectation because it is known. If I know the time TB, if I know the first hitting time, then clearly I know the value of this indicator. If I know the value TB, then I can judge whether it's smaller than T, in which case the indicator is 1. And if the value of TB was exceeding T, then that indicator is 0. And so that's the reason for me being able to take it out and simplify the problem into kind of 2 separate components. That's what's being, that's what the kind of the goal here is to split something complicated, the product of two things, and treat them one at a time. And of course, this inner expectation can be written as just some function of the random variable, the random time that we have. That's what a conditional expectation is, and here is just me writing it in terms of some prescribed value little s. So I can plug in anything now for the hitting time and have it be the same expectation. So this is just kind of the redefinition of the function g, plugging in any particular value of the hitting time that I want it to have. And now we kind of look at this and we think, well, what is TB equals S? What does that really mean? It's basically what does it mean that the hitting time of the Brownian motion occurred at time S? Well, a couple of things had to have occurred, had to have happened in order for this to occur. One is that the Brownian motion at time S better be equal to B. That's what it means. At that, this is the illustration here. At the time at which the Brownian motion hits the level, the Brownian motion better be equal to that level. That's by definition. It's also because the Brownian motion is continuous. If the Brownian motion did not have continuous paths, then maybe we would not necessarily be able to state this, although that depends. So here, by continuity of the Brownian motion, it has to be in state B at the at time S, which is the hitting time. And that's clearly not the only part of the definition of the hitting time. Not only does B have to be at the level that we want to hit, it also has to be true that it was the first time that this happened. And so I've appended here the condition that the Brownian motion at all times u, for all u before S, so everything past this point, this would be the u, everything before this point, the Brownian motion had to be strictly below the level B, which is what you observe. And this, kind of just these three sort of statements basically encapsulate the definition of the first hitting time. It has to be at the level B at the actual time S, and every single value before has to be strictly below that level, meaning it's the first time that we hit the level B. So now continuing on, I'm just transitioning here to the same exact thing but written in probabilities. So expectation of the indicator is the probability of the event, and here I've applied the Markov property. So everything before that came before time S is irrelevant by the Markov property of the Brownian motion, and this allows me to drop this part right here. So everything there goes away, leaving me with this, which in fact is an increment. That's what this is. It's b at time S minus b naught. And what do we know? We know that increments are independent, so there's, I guess, one more thing that happened in here. Because b at time S is equal to b, I moved this b over to the other side, so I moved the b over here and let it be equal to bs, which is exactly what you see here. So when you see this probability or any kind of expectation, and you're given that the random variable is equal to some number, I can either put that value in, or I can put the random variable in. It is the same exact thing. And that's what happened going from this line to this line, moving b over to the other side, so to get b at time t minus little b is greater than 0, and then substituting for little b the actual notation for the process. But these two probabilities are the same. And finally, this is an increment, and it's an increment that's independent of this one. The increments are not overlapping and therefore independent by the property of independence of increments of the Brownian motion. And finally, you see that if you're conditioning on something that's independent of the thing that you're either computing an expectation or the probability of, you can drop it. It is irrelevant as far as that probability or expectation is concerned. And then finally, what is this distributed as? Well, it's mean zero normal with variance t minus s, and the variance is sort of irrelevant. What's the probability that a mean zero normal random variable exceeds 0? Well, it's 1/2. Half probability is on the left. It's a symmetric, in other words, it's a symmetric distribution. The normal distribution is symmetric, and so it's equally likely to be on one side or the other. So I mean, at this point we're almost at the end. Let me think what we need to wrap up here. I mean, one thing to do is to take sort of this partial result. We've just computed the function g of s. So one thing you notice is that regardless of the value of s, the value of the function g is 1/2. So it doesn't matter what time here I feed it, whatever, this function just always maps over to the value 1/2. And so if I just substitute 1/2 for this conditional expectation, and this is the kind of the key part of the proof here, all of this complicated business becomes just 1/2, leaving me with an expected value of the indicator of the hitting time being before time t, and that's just the probability. So now, the logic went from this probability, from this side, from the left side here to the right hand side, then it went to here to there. 1/2 was substituted into this, was replaced this conditional probability, leaving me with that times 1/2. And you can see how this is, in fact, the reflection principle. It says that the probability that the hitting time occurs before time t is twice the probability that the Brownian motion exceeds the level b. And the reflection principle, where did it play a role here? Well, you can almost kind of guess why this had to happen. If you look at this probability here, it says that the hitting time was before time t, so let's say it was somewhere here, and the Brownian motion at some potentially future time was above the level. Well, it would have been equally likely that it went below. In other words, both of these trajectories have the same exact chance of happening. Once the Brownian motion is located at this point, its transition probability depends only on the value here, and to think about how the random walk was moving, it either moved left or right with equal probabilities, and so it would transition either this way or that way, and both of these paths mirror each other, but they're quote unquote equally likely. That's sort of the intuitive way of understanding what happened here. That's exactly why we're able to assign a probability of 1/2 here. The probability that given this occurrence that it went above is just as likely as if it went below, and hence reflection. I tried to draw this as best as I could, so kind of a reflection around the level B. There are a couple of I guess more things to, maybe just one more thing to say. The reflection principle has this sort of extra part to it, which equates not just these two probabilities, but also equates this one, the one of interest, to this probability in terms of the maximum of the Brownian motion. And that's easy to see why. So in fact, this event and this event are one and the same. So let's think about it. In order to argue that the two events are identical, you have to have conclusions both ways. So here we've, for example, argued that if this, then this, giving us that this event is a subset of that event, but we saw that the converse was false. Let's see if that happens here. So let's assume that the hitting time came before time t. If the hitting time is before time t, then this says that the maximum of the Brownian motion by time t, that's what this m is, has to be above the level b. So Why is that? Well, if the hitting time came before, then it must have already hit the level B, and then potentially it could have gone even higher or it could have gone lower. It doesn't matter. The maximum was still recorded at the level B, and whether it exceeded it further or not is not really what's being asked. What's being asked is whether that maximum is at least B, and because we've already hit the level B, that must be the case. So that's the application going from this direction to this direction. We now know that TB less than T is a subset of MT greater than B. And now to go the other way, if we know that the maximum of the Brownian motion exceeds the level B by time t, then what do we know? Well, then certainly the Brownian motion, if the maximum is exceeding the level B, then at some point before time t, the Brownian motion had to cross this level. Otherwise, the maximum would have been below the level B. And so you have the opposite inclusion. MT greater than B implies TB is less than T. And once the two sets are equal, so now we went this way and that way, as opposed to these two events are one and the same, and therefore their probabilities are the same. So now not only can you get the distribution of TB, you can also get from this the distribution of the running, what's called the running maximum of the Brownian motion.